Hey everyone, I'm Akash Joshi, I'm the OR Guru, and today we're going to be talking about the facility location problem, which is a famous operations research problem. So in this video, we're going to be using integer programming, which is a branch of operations research, and the facility location problem answers the question, where do I build facilities to meet demand while optimizing or maximizing profits? When I say facilities, I mean a factory, a retail store, anything that's trying to meet demands. So there are three types of facility location problems. The first one is the set covering problem. In this one, the idea is to build the least number of facilities to cover all the demands. The second type of facility location problem is the maximum covering problem. In this one, we're going to try to build a certain number of facilities to cover the most amount of demands. So the amount of facilities we're trying to build is already given. The final type of facility location problem is the fixed charge location problem. In this one, we're going to try to balance the benefit of covering demands and the cost of building facilities. So the idea is that we're going to combine the previous two problems and we're going to balance the benefits and costs while maximizing profits. First, we'll focus on the set covering problem. I'm going to define the problem for us. The question we're trying to answer is, where should I build the least number of facilities to meet all the demands? In set A, we have our demands A. In set B, we have our possible locations B, where we can build our facilities. I've drawn a model here, and the green squares are places where we can build locations to meet demands, and the red dots are all the demands that we have to meet. Keep in mind that the green locations over here are just possible places where we can build them. We don't have to necessarily build anything in that area. So the distance between demand A and location B is denoted as DAB, and it has to be greater than 0 because distance is always positive. And A is an element of set A, B is an element of set B. M is a constant, so M is the maximum amount of distance allowed between a location and a demand. So demand A is covered at location B if DAB is less than M. If M is equal to 50 miles, let's say, this is 25 miles away, so this location meets this demand. But over here, this location over here is about 75 miles away from this demand. So this location does not meet this demand. So what I've done here is I've just defined the problem. I've given different letters and assigned them as variables or constants. Yeah, so now let's complete our formulation. Actually, I forgot to define our parameter and our decision variable, so let me do that right now. Our parameter is YAB, and we're going to set it equal to 1 if the distance is less than the maximum distance allowed. And we're going to set Y equal to 0 if the distance between the location and the demand is greater than the maximum distance allowed. So if we set it to 0, this means that it'll eliminate this this connection, this link between the location and the demand. It'll eliminate it from the formulation, and it won't be factored in when it gets summed up. And of course, this is for A as an element of A and B as an element of set B. So that's our parameter. Next, I'm going to talk about our decision variable. So our decision variable is going to be XB, and we're going to set it equal to 1 if a facility is built at location B of set B, and we're going to set the decision variable to 0 if no facility is built at that location, at that possible location. If we set it to 0, it'll also eliminate it from our formulation, from our sum, because it'll be 0 and it won't be factored in. Once again, here is the drawn out model of our problem. Now I'm going to talk about our complete formulation. So our objective function is that we're trying to minimize the number of locations that are being built, but we're also trying to make sure that all the demands are met. And our objective function is to minimize the sum of xb, and we're going to set xb equal to 1 if a facility is built at location B of set B, and xb is going to be equal to 0 if no facility is built. So we're going to add up all the ones and zeros, and we're going to try to minimize we're going to try to minimize the sum. So if this location is x1 and we choose not to build anything there, then x1 is going to be equal to 0. If this is x7 and we choose to build something there, it's going to be equal to 1. So we're just trying to minimize the number of locations being built. To summarize, this is our objective function, and we are trying to minimize the sum of xb, which is the total number of facilities built. Next, we have our constraints. This summation right here, this summation means that among all the possible facilities being built, at least one facility must be built to cover a specific demand at node A. In other words, at least one distance between one of the built facilities and the demand has to be less than m, which is the maximum distance allowed. So at demand A, at least one facility must cover the demand within distance m. These constraints right here simply mean that xb is either 0 or 1, and yab is either 0 or 1 for all values of a and b. To conclude, this is our complete formulation right here. We simply have to input this into Excel or programming language, and we'll have our optimal solution. I may make a video later on how to do that and how to get the optimal solution from Excel or the programming language. Up next, I'm going to explain the maximum covering problem. So the question that we've been assigned to solve is that given that I have to build a specific number of facilities, how can I cover as many demands as possible? So keep in mind here that you won't cover all the demands necessarily like you did in the last problem, in the set covering problem. You just want to cover as many demands as possible, given that you have to build a specific number of facilities. So like in the previous problem, you have a set of demands A in set A. You have a set of possible locations B in set B. The distance between demand A and location B is DAB, which is greater than 0. A is an element of A, B is an element of B. M is a constant. Demand A is covered at location B if DAB is less than M, so M is the maximum distance allowed between a demand and a location. If DAB is less than M, the facility covers that specific demand. So this is nothing new. I explained this in the last problem. Also, what we had in the last problem, we also have in this problem. We have a parameter YAB, which is the covering coefficient. YAB is equal to 1 if DAB is less than M. YAB is equal to 0 if DAB is greater than or equal to M. A is an element of A. B is an element of B. Our first decision variable is the same as in the last problem. If xb is 1, a facility is built at location B. If xb is 0, no facility is built. In this problem, we have a second decision variable called ZA. If ZA is 1, the demand A of A is covered by a facility. If ZA is 0, the demand A of A isn't covered by any facility. Keep in mind that this is any facility and it is different than YAB because YAB is between a specific location of a facility and a specific demand. Meanwhile, in this ZA variable, we are only considering if the demand A is met by any facility at all. Also, at most, we can build n facilities. N is a natural number, so 0, 1, 2, 3, it cannot be a decimal. It's just good to include that so that we don't have to worry about non-integers. Okay, so our objective function is trying to maximize the number of demands met. This summation constraint down here is implying that the total number of facilities built cannot exceed the maximum number of facilities that we are permitted to build. These constraints over here simply mean that XB, ZA are both binary and they're either 0 or 1 because that's what binary means. And then this constraint over here is the main constraint of the formulation. What it's saying is that if ZA is 1, the left-hand side, or the sum of the products of both the covering coefficients and XBS at each facility, the left-hand side or that can either be greater than 1 or equal to 1. If the left-hand side is 0, then ZA must be 0 because obviously the demand is not being met. And this constraint is for all values of A of set A. Next is the fixed charge location problem, in which you're trying to balance the cost of building a facility and the benefit of covering demands. Actually, I will be explaining the solution to this problem in a later video, so it's coming soon. That's it for today. All right, y'all, see you.